Hey, welcome here to chapter 3. This is going to be a pre-recorded lecture to try to keep us back on pace due to the holiday that we had. So chapter 3 here covers matter and energy, and some of the topics here we sort of talked about earlier on in the semester here about matter. We're going to go into a little bit more detail here one more time. So let's get started. So obviously matter and energy. Matter is really, as we talked about, I think earlier on, maybe in the first chapter as well, matter is really anything that has mass and occupies space. So essentially that's pretty much almost everything that we kind of come across. And as we also talked about earlier on, there's kind of three states of matter, which we'll go into a little bit more detail here in this chapter: solid, liquid, and gas. So these sort of three states of matter are things that we commonly come across in chemistry. And a lot of things that we do involve really the transition of matter from sort of one state to the next. So let's talk a little bit about matter. Matter, as I just mentioned, basically occupies space. It makes up pretty much everything that we use. So water, wood, air, plastic bags. We can classify matter according to its composition. We really could have something that's a pure substance. And a pure substance is something that has a fixed or definite composition. So for example, if you had water by itself, H2O, that is a pure substance. You have just water, nothing else there. That is definitely a pure substance. Now, when we take two or more pure substances and put them together, we get what is referred to as a mixture. And a mixture is basically a combination of two or more pure substances together. The key thing about a mixture, though, is everybody still retains its identity, which means they are really put together more with a physical change, as we'll talk about, rather than any type of chemical reaction taking place. Sometimes, though, when we have a mixture, we sometimes think that a chemical reaction is taking place because perhaps we can't see one part of the mixture. So for example, if we take our water here, which is a pure substance, and we also take some sodium chloride, which is a pure substance as well, that is salt. Each of these individually are pure substances, but if we were to put these together, we would make salt water, which is a mixture. Now, as I was mentioning before, even though when you look at something like salt water and you just kind of look at it, it looks like pretty much just water's there and the salt's like gone. It just disappeared. And again, it really didn't disappear. It's still there, even though we can't visually see it. And as we'll talk about here in this chapter as we go through, what's essentially happened is basically all the salt gets surrounded by a bunch of water molecules, which makes it pretty much sort of invisible, if you will, to our eyes. And that's basically the process of something dissolving. So water by itself, pure substance; sodium chloride by itself, pure substance. If you had just a piece of copper metal by itself, pure substance. But if we take those things and put them together, for example, like the water here and the salt, we get a mixture. But again, the key part about a mixture is it's still able to retain its identity. So really, matter can be broken up into several parts here: pure substances that can be elements or compounds. And I think we also talked a little bit about sort of the differences here. An element is our basic unit, which are represented by atoms is the basic unit of an element. So really atoms, which contains protons, electrons, and neutrons, are the basic sort of unit of an element. Element is really as far back as you could go. You can't really go any further back. So kind of like the alphabet, there's only like 26 letters. The elements, there's only so many elements, but different combinations of elements can produce compounds, and compounds are really two or more atoms of different elements that have basically come together. We could definitely take compounds, as we will talk about back to elements, but pretty much as far back as you could go are the elements. We could take compounds back to elements through some type of chemical process, chemical change, chemical reaction. But again, as far back as you could go, there are elements. As we'll talk about here with mixtures, there are actually two different types of mixtures, homogeneous and heterogeneous. And we'll talk about sort of the differences between those. So let's talk about each of these things here. A pure substance is classified again as a type of matter that has a fixed or definite composition. An element, again, is basically as far back as you could go in terms of matter. It is basically represented or composed of atoms. Atoms, as we'll talk about, have even smaller structure. It has protons, electrons, and neutrons. But as far back as you go, there are your elements. A compound is, again, always composed of two or more elements that are combined in the same proportion. For example, water here is a compound. It is made up of hydrogen element and oxygen element. And a word that sometimes is confused, and I think we might have touched upon it, but just in case we didn't, is compound and, say, molecule. Now, a molecule is simply the combination of two or more atoms together. And the reason that's sort of different than compound is a compound is two or more atoms really of elements, two or more different elements that are together. And that's a big key, because if we take something like H2, which is basically two hydrogen atoms bonded together, H2 is a molecule. It is a diatomic molecule. But because H2 is only composed of one element, it is also considered an element as well. So H2 is an element. H2 is also a molecule, but H2 is not a compound because H2 only contains hydrogen. Now, by the same token, if we look at water, water is a compound, as we talked about, because it does contain both hydrogen and oxygen. Water is also a molecule because it meets the basic definition of two or more elements that are together, atoms of elements that are together. So we have hydrogen, oxygen, and hydrogen all bonded together. So that's at least two atoms. So it is a molecule as well. But water is not an element because obviously it contains two different elements there. It contains both hydrogen and oxygen. So sometimes people get confused the idea of what's the difference between a molecule and a compound. You can think of a molecule as sort of a generic term for two or more atoms together. And those atoms can be the same element or they can be different elements. While a compound is basically two or more atoms together, but a compound needs to be at least two or more elements involved in that for it to be a compound. Now, elements are pure substances that basically only contain one type of material. As we can see here, if we have just pure copper, it should only contain copper atoms. If we have pure lead, it should only contain lead atoms. And if we have pure aluminum, it should only contain pure aluminum. A compound here, some other examples, what they all really share in common is, again, hydrogen peroxide, two elements. We have our hydrogen and our oxygen. Sodium chloride, an ionic compound, sodium atom, chlorine atom, carbon, hydrogen, and oxygen here in sugar. And then obviously we talked about a second ago there, water, which obviously has hydrogen and oxygen. So all these things that we see here could be classified as compounds. For the most part, all these things here could be classified as molecules as well. So this would be classified as a molecule. This one would be classified as a molecule. This one would also be classified as a molecule. Technically speaking, this one here, and as we'll talk about in some later chapters, is an ionic compound. And kind of by that definition of ionic compound, which basically means sort of held together by positive negative attraction, as we'll talk about when we get into sort of naming and things of that nature. Most people would not necessarily call sodium chloride a molecule because in a lot of cases, people think of molecules as the idea of what's referred to as covalent bonding, where we have sharing of electrons. So some people will call it a formula unit because it's ionic, but you don't have to worry too much about that. But basically, a molecule is oftentimes sort of reserved for definitely two or more atoms together, and usually more so the covalent type of compound. I'm sorry, covalent type of a molecule where we do have sharing of electrons. Now, here's sort of my earlier example. Obviously, table salt is a combination really of two different things. It is sodium metal, which, as we can see over here in this picture, looks like a piece of metal, and a pretty toxic chlorine gas, green toxic gas. Through the miracle of science and chemistry, we get some sodium chloride, which is a compound. Also brings up a very important point. Clearly, as you can see here from this slide, usually the properties of a compound are very different than the properties of the elements that make them up. These are really the elements here. And obviously this is our compound over here. Clearly, we would not want to put a piece of sodium metal on our fries. We wouldn't want to put some toxic green chlorine gas on our fries. But again, through that miracle of chemistry, maybe we want to put salt on our fries. It's okay. Now, let's talk a little bit about mixtures. Mixtures, as I mentioned, are really when we take two or more pure substances together and combine them. The key is, though, that each of them, of the pure substances, although they are combined in a mixture, still are able to retain their own identity. Again, as we talked a little bit earlier about sort of the salt water, it may not visually be able to see those guys, but they are still there in their original form. The other important part of sort of a mixture is you typically can separate back out all of the pure substances by some type of physical means. So they retain their identity. We're able to really separate out all of the components of a mixture by physical means. What are physical means? You know, boiling, filtering, separation, but we're really able to separate everybody back out, and you could essentially retrieve all of the different parts of the mixture really back to their original form. And we'll talk a little bit about that here in just a second. So for example, here is a way that we can separate out a mixture. We could do a process known as filtration. Filtration, we have a funnel, we have filter paper, and obviously we have some type of collection beaker here. We're pouring this through, and filtration works really well to separate out a solid from a liquid. And that's because when we pour this, almost looks like orange juice, but it's not. It's actually lead to iodide. But that yellow, which you can kind of see right there, all that yellow is really a precipitate or a solid, even though it may not appear to be kind of small forms. And here, I guess I'll grab the right color to correspond to what they're pouring through there. So what will eventually happen is all that yellow will basically be caught right there in the filter paper. And obviously the liquid component will find its way through and basically end up over here. And now through this process, we have now separated out the solid from the liquid. And we now have both parts of our substances, our pure substances back. We could take out the filter paper, kind of spread it out, put it into an oven. We could dry it out, and then we would have pretty much solid that yellow precipitate there. Obviously, we have the liquid component there, just like it was originally. Here's another one. This is chromatography, which is a way we use a solvent, and it does sort of separate out a mixture by how it travels. The solvent sort of helps it do that. kind of attracted to it, and we really separate out these sort of guys. Now let's talk about really the different types of mixtures that we come across. One is a homogeneous mixture. A homogeneous mixture is a mixture where after sufficient mixing, everything looks the same throughout. So salt water is a very good example of that. Clearly, if you grab, say, some water, maybe from the ocean, you just grab the water. You look at it and it just looks like H2O, just plain old water. Obviously, if you taste it, you shouldn't drink ocean water, obviously. But, if you taste it or something like that, it is salty. And there is definitely salt in there. You can't visually see it. Same idea, if you took a little salt and you put it into a cup of water, and kind of mixed it, it would dissolve. You took a little bit of sugar, for example, and also put it into like a cup of water, it would dissolve. And again, when you look at that, all you really do see is sort of the liquid part, the water. And it appears like perhaps, the salt has completely disappeared. It has gone somewhere. It has reacted away, is sometimes what people think. But it's really not. It's really just surrounded by a lot of water molecules. So for example, when you put something like sodium chloride into water, sodium chloride, which is salt, is basically made up of two ions. It's made up of a sodium ion, and it's made up of a chloride ion, which is negatively charged. And when you put it into something like water, and as we'll learn in a later chapter as well, water actually is what's referred to as a polar molecule, which basically means that there's a side that's more positive, which is the hydrogen side, and there's a side of water that's more negative, which is the oxygen side. And in chemistry, there's opposites attract. So basically what happens is a bunch of water molecules start to surround all the sodium ions that are there. And they actually surround it by lining up their oxygens near the positively charged sodium ion. And that's because opposites attract in chemistry. So the negative side of water attracted to the positive side of the sodium ion. Chloride, which is negatively charged, also gets surrounded by a bunch of waters, but it actually gets surrounded by the hydrogen side of water. And that is because the hydrogen side of water is essentially the positive side. And what ends up happening is, before you know it, they get surrounded by a ton and a ton of these water molecules. And visually speaking, when we look at it, we're not able to actually see the sodium chloride anymore. So that's why sometimes people think it obviously chemically reacted away. And the answer is it really didn't, because you could do a simple process where you could take this sodium chloride, for example, that's in solution. You could put it onto something like an evaporating dish, right? And you could start to heat it. And as you start to heat something like salt water, the water part's going to start to evaporate. And what that's really doing, if we kind of go back to this little drawing I did over here, is as you start to heat the water, all of a sudden you're starting to drive off all of these waters that basically surrounded these ions. And before you know it, you get rid of all the water that's there. There's going to be absolutely nothing left to prevent these two guys from coming back together. And they will come back together as that ionic solid. And that's what would happen here in this evaporating dish as we continue to heat and heat and heat. Eventually, at the end, really the only thing left in our dish would be probably a white residue if it was sodium chloride, but we would have sort of that white residue of solid that would be there. And through this process here, we've actually just separated out our homogeneous mixture. We didn't actually collect the water part, but the water part is really here in the steam that's coming off. And then obviously we get our sodium chloride part. And that's a very common way that you can separate out a homogeneous mixture, is a process like this. There's also a process where you can actually, if you wanted to, collect the water back. And I'll do a really bad drawing here, but we'll kind of do kind of a closed system, if you will. And what connects these two systems is something that's really cold. And if you take your salt water over here, and again, you heat it, and again, in a closed system, we're going to get our steam that's going to occur. Now, steam, when it hits this really cold water, is going to go through condensation and go from the gas state back to the liquid state. And before you know it, you will then get your liquid water happening on the right-hand side. And again, if you continue to heat the left-hand side, eventually you will drive off all of that water. And on the left-hand side, and hopefully you don't erase the whole thing like I just did there. Let's rebuild it real quick. What will be left on the left-hand side after sufficient heating would be, again, your salt would be left over. So through this process here, we have now recovered the salt. Through this process here, actually, we could just call it water. And we've now recovered both the water and the salt in their original forms. Again, you could take the salt, let it dry out, and you would have your salt just like it started with. And obviously you would have your liquid water. This process is what is referred to as distillation. And again, a very good process to separate out homogeneous mixtures. So homogeneous mixtures, again, are these mixtures that we basically, when we mix it, everything mixes really well. It all looks like, sometimes people refer to it as one layer, one phase. You really don't see the different components, and that's a homogeneous mixture. Here's some examples of some homogeneous mixtures. Again, obviously your scuba gear in the tanks. The other type of mixture is a heterogeneous mixture. In a heterogeneous mixture, when we mix the substances together, we actually do see different layers. So we do see distinct different layers. We visually can see that, and that's a heterogeneous mixture. For example, if we took some sand and water, right? So water and sand, you can mix that thing all day and you'll never get the sand to dissolve in the water, right? And you will still visually be able to really see the sand that's in there. And that obviously is a heterogeneous mixture. It looks like here they threw some pennies into water, and clearly if you threw pennies into water and you mix it up a lot, you definitely would still be able to visually see the pennies. Chocolate chip cookies, right? You see the chocolate chips in there, in the cookie as well. And other common one is if you took some sand, maybe you put some pieces of metal in it. Again, if you take those metal pieces, you can mix all day. You will definitely see the different components. So a good way for a heterogeneous mixture to separate out is what we saw earlier, and that's through filtration. Is a really good way to separate out a lot of heterogeneous mixtures, and especially solid and liquids. It's a very good way of doing that. Again, with a funnel, some type of filter paper. And again, the solid gets trapped up on top, and obviously the liquid component can go through. So let's take a look at these and see which one is a pure substance or a mixture. So take a moment here and see what you come up with. Okay, so we have pasta and tomato sauce, aluminum foil, helium, and air. So pasta and tomato sauce should be a mixture. Aluminum foil, if it's pure aluminum, should be a pure substance. Helium, which is an element, would obviously contain only atoms of helium, which would make it a pure substance. And air is actually a mixture. Major component of air is nitrogen gas, actually, followed by oxygen gas and other things depending on where you're breathing the air. But it's actually a mixture of a bunch of different gases. Let's take a look at each of these. Are these homogeneous or heterogeneous mixtures? So take a second here and see what you come up with. Okay, so let's take a look at it. So hot fudge sundae is a heterogeneous mixture. I'm assuming there's some like hot fudge, there's some nuts, there's some whipped cream. Sounds good right about now. Baby shampoo, again, if you look at baby shampoo, or really most shampoos, I would think, it does look the same throughout. It doesn't look like there's any other components in there, so that would be a homogeneous mixture. Sugary water, again, if you take a little bit of sugar and put it into water, that sugar will most likely dissolve. So when you look at it, it will only look like obviously water that's there. So homogeneous mixture. And peach pie, I'm assuming they're talking about a pie where you actually have slices of peaches in it. And obviously, if you cut it open and you look at the inside of the pie, you could probably see the pie filling. You could also see probably the peaches in there or whatever else you may put in there. And obviously those would be heterogeneous mixtures. So let's then talk about some of the states of matter, which again, I believe we have touched upon solid, liquid, and gas. But let's just start with solids. Again, to remind everybody, solids have a definite shape and a definite volume. The particles are held really closely together by attractive forces. So, when we think about things that are solid, we think about things that are packed in there pretty tight and dense to one another. And because they're really packed in, they're pretty tight to each other, they don't really have enough energy to sort of pass one another. So those guys sort of really lock into place. And if you think about things, they're sometimes referred to solids as being rigid, which means it's very hard to change the shape of it. If you think of like a table, you can't really just easily take a table and like fold it over or anything like that. It's very rigid, it's very hard, and very hard to change the shape of it. Now, most things in their solid state are more dense than in their liquid state. And I think we might have touched upon it with density in the previous chapter, but water is an unusual example of that. Water actually, when it comes together to form ice in a solid state, has an unusual property that the molecules actually don't get really close to one another. Actually creates a lot of empty space between the different water molecules, which is why when we think about density, for example, water, ice is actually less dense than liquid water, and why when we put ice like in our soda drink or soda or any drink really, ice usually ends up floating to the top because it's less dense. But most things in their solid state are usually more dense than, say, in their liquid state. So let's talk a little bit about liquids. Liquids have a definite volume, but not a definite shape. They really do take the shape of their container. And what that really means is, again, if you had 10 milliliters of water, and you put that 10 milliliters of water into a test tube, it would take obviously the shape of the test tube. You take it out and you put it into like a soda bottle or something like that, it would take the shape of the soda bottle. You put it into one of those crazy straws or something like that, right? It would obviously take the shape of the crazy straw. What it means about a definite volume is that if you did start with 10 milliliters, say, of water, and all the examples I just drew there, and you transferred it from one container to the next, you should still have 10 milliliters of water, as long as you're not a klutz and spill it on the floor or anything like that. But you should definitely still maintain that 10 milliliters of water. Particles in the liquid state, though, do possess enough energy to sort of slide by one another. And that's why when we think of the liquid state, it is more fluid, obviously, than the solid state, right? And that's why liquids are fluid, because they do really possess enough energy to sort of pass one another. They are still relatively, sort of packed in there pretty tight. But again, in this case, they do possess that energy to sort of slide by one another, and that creates sort of a fluid liquid. Now, sometimes while we're talking about liquids here and which sometimes has the L abbreviation. Sometimes people wonder what is the difference between that, say, and something with the AQ abbreviation, which is known as being aqueous. And there actually is a difference between these two. So, for example, a liquid is a pure substance like water. So if you had water just by itself, that would obviously get the liquid sort of symbol. But if you make a mixture like we were talking about earlier, a homogeneous mixture where we took like the sodium chloride and put both of those guys together, again, the sodium chloride would dissolve in the water and we would get a sodium chloride that will get this symbol, which is the aqueous symbol. And that basically means that we made a solution. So there is a difference between those two symbols. And sometimes people get confused as we go through some of these chapters here. You know, what's the difference between a liquid and what's the difference between an aqueous solution? And the difference is typically when an aqueous solution, you take something and you dissolve it in a liquid like water to make a solution. So really a solution that has the AQ symbol is really a homogeneous mixture. And that is different than if you had a pure liquid. So again, if we have water by itself, that is a pure liquid. If you had salt water, that's really not a liquid. You know, it is in the liquid state, but technically when it get the liquid sort of symbol, it would get more of an aqueous symbol next to it to imply that it was basically made as a solution in a mixture. Now, gases have an indefinite shape and an indefinite volume, and they do take the shape and volume of their container. They sometimes are referred to as filling their container sort of uniformly. And that's because in the gas state, we have completely broken apart everybody. Everybody's flying around. As there is collisions, that is what we associate pressure with in terms of our gases. And it does fill the container uniformly. In fact, as we talk about in terms of gases in a later chapter, one idea of a gas is that, you know, we don't really look at the volume of a gas, but we think about the gas's volume as the volume of the container because they are constantly flying around, colliding and so forth. So they sort of represent really the entire volume of the container they're in. So we have gases that are flying around, and here's sort of a table of some of these different properties that we talked about: solid, liquid, and gas. As we also talked about before, right, as we transition from one state to the next, there are sort of names that are associated with that. So as we go from solid to liquid, that is the process of melting. As we go from liquid to solid, that is the process of freezing. Liquid to gas, that is the process of evaporation or vaporization. Gas back to liquid is the process of condensation. Solid skipping the liquid part and ending up at the gas part is sublimation. Oops. Gas skipping liquid and going back to solid is the process of deposition. And these processes do, let's move a couple of things here out of my way. There we go. These processes here do require a certain amount of energy that we're going to talk about a little bit here in this chapter. Again, as we go from solid to liquid to gas, we do have to put energy in to do that. And that is what is referred to as an endothermic process. And opposite is true as we go from gas back to liquid, back to solid. That is where we have to actually release energy. And that is a process known as being exothermic. I think we might have also touched upon it as well, and we'll talk about it, I think, here in this chapter as we continue through. These processes here occur at the same temperature, and these two processes here also occur at the same temperature. So, you know, when we do sort of melting or freezing occurs at the same temp. and evaporation or condensation also occurs at the same temperature. It really depends in terms of energy, what you have going on. If you continue to kind of put energy in as you go from solid to liquid to gas, then you'll continue that process of really melting to evaporation. If you continue to take energy out as you go from gas, the gas molecules basically slow down. They no longer have enough energy to escape each other. They kind of fall into the liquid phase. If you continue to take energy out of liquid water, like you put it in the freezer, you then will have guys that no longer have enough energy even to kind of pass each other, and it will go into the solid phase. So let's take a look at each of these here. Identify these as solid, liquid, or gas. So take a second here and we'll go through it. Okay, let's see what we got. So has a definite volume but takes the shape of the container. That is definitely a liquid. Particles that are moving rapidly. Again, that's the gas phase, basically bouncing around, moving around, collisions. Particles fill the entire volume of the container. Same idea. That is our gases. Again, because they're constantly flying around, it is thought that they really fill the entire volume of their container uniformly. Particles have a fixed arrangement. That is solid, fixed, and rigid, right? That is a solid sort of description. And particles are close together but moving randomly. That is liquid. So again, in the liquid phase, they are still relatively close to one another, but they do possess enough energy to sort of slide by one another. And again, as we talked about, why we think about liquids as being sort of fluid. Let's take a look at this one here. Identify the state of matter for each of the following. So take a second here. Is it a solid, liquid, or is it a gas? All right, let's take a look at it. So vitamin tablets, I'm assuming, should be solid. Eye drops should be liquid. Same thing with our vegetable oil, should also be a liquid. Candles are usually solid until you start melting them. Then obviously air in a basketball is a gas, right? So as we fill up a basketball with air, right, we're putting gas molecules in there. As they're flying around, right, they're causing a certain amount of pressure, which will keep, say, your basketball not flat, but able to be solid and basically able to bounce. Let's talk a little bit about some of these properties that we've sort of been talking about. Physical properties. Physical properties usually accompany, as we'll see, sort of physical changes. And physical properties are really characteristics that are observed, are measured without changing the identity of a substance. They include things like physical states. So is it solid? Is it liquid? Is it a gas? Those are very common sort of physical properties. Things like boiling points, freezing points, things like density, things like color are all physical sort of properties. For example, copper, these are all physical properties of copper. It's reddish orange, it's shiny. It's a metal, which means it's actually a good conductor of heat and electricity. It's a solid, and they're melting and boiling points. Now, physical changes occur when matter undergoes some type of physical change, but the really important part of it is there is no fundamental difference in the substance you started with and in the substance that you ended with. So what that means is, whatever you started with, it may have changed shape or something like that, but it is still essentially the exact same substance. For example, if you took a peanut and you crushed the peanut, you now have crushed peanuts. But fundamentally speaking, a whole peanut and a crushed peanut is still fundamentally the exact same thing. There has been no real change in what that substance was. Water is a very good example. If we have ice is really water, H2O, in its solid form. If we have liquid water, it's obviously H2O. in its liquid form, and steam, which is what we commonly call water in its gas phase. But steam is still H2O. So if you did that process of taking an ice cube out of the freezer, letting it melt into liquid water, and then heating that liquid water up till it evaporates off as steam, those are all physical changes, because in all three of those states, solid, liquid, and gas, in the case of water, they're all still fundamentally H2O. So sometimes people think, that process is a chemical change. Again, it is not a chemical change. It is a physical change. And a physical change is exactly what we were talking about with mixtures. Those mixtures were all physical changes because we could simply take those mixtures and separate them out and get back our original substances. So even though we can't visually see it, like the salt example in the salt water from earlier, we can't see the salt anymore. It was still there, and it was still there in its original form. And we're able to do that by simply evaporating off the water. So when we talk about mixtures, again, those are physical type changes that are occurring. The physical appearance of a substance can also change with a physical change. For example, again, the salt dissolved in the water, salt crystals are no longer visible, but definitely can be reformed, as we talked about. So let's take a look at each of these. Classify each of the following as a change of state or a change in shape. So chopping a log into kindling, water boiling, ice cream melting, ice forming in the freezer, and cutting dough into strips. So take a second here. Are we changing the state or are we changing the shape here? And the answer for these is obviously if we're chopping something up, we're changing the shape of it. When we boil water, it's going to create steam, which would be changing the state, going from liquid state to gas state. When ice cream melts, that is changing the state. Sadly, that is our solid ice cream that is now liquid ice cream and probably making a mess everywhere, I imagine. Ice forming in the freezer, that is also a change of state. We're going from liquid water back to solid water in the form of ice. And cutting dough into strips would be just changing the shape of it. Again, all these would be physical types of changes. Chemical changes, on the other hand, really do follow sort of chemical properties. And chemical properties describe really the ability of a substance to kind of do two things: really react with something or even resist a reaction. So a chemical change usually involves a change in fundamentally what you start with. So you start with something and you go through this chemical change and you end with something that is fundamentally different than what you started with. And you cannot, by any type of physical means, get back your original substances. So for example, if we took water and we do an electrical current over it, we actually will break apart water into hydrogen gas and oxygen gas. You take the hydrogen gas, take the oxygen gas, and do a whole bunch of stuff to it, but it will not physically, by any type of physical means, go back to water. You would actually need a chemical reaction to make it go back to water. And that's, again, an example of a chemical change. If you take a little bit of iron metal, a little bit of oxygen gas, and a little bit of moisture, basically, that is enough to then kind of fuse the iron to the oxygen and make rust, basically, iron 3 oxide. It will make rust. And in that case, the iron and the oxygen are now sort of fused together chemically. And again, if you've seen anything that's rusted or whatever, you can't do any type of physical means to get back the iron or the oxygen. You can't put the rust in the freezer to get it back. You can't heat up the rust to get the iron back or anything like that. The chemical changes definitely occurred. So the big difference between chemical change and physical change is, in a chemical change, what you start with and what you end with are two fundamentally different things. While in a physical change that we talked about earlier, what you start with and what you end with are fundamentally still the same thing. So we see new composition, new physical properties, new chemical properties. Caramelizing the sugar there at high temperatures on our dessert over there, again, is a chemical type of change. Here are some examples from a table from your book of physical changes and chemical changes. Again, water boiling is just a change of state. You could draw copper into wires. You could draw them, make pretty knots with the copper, I guess. It's still copper wire as long as nothing happened to it. Sugar dissolving in water to form a solution, which is a homogeneous mixture, is a physical change. And then here's on the other side some of our chemical changes. Silver tarnishing from the reaction of oxygen sulfur. When you burn a piece of wood, obviously it changes to ash and a whole bunch of things. If you put a log into the fireplace and let it burn, at some point, all the stuff is made. You can't collect up and put it back together physically to get the log back, right? No way to do that. And obviously that is a chemical change. And again, here's a table of some different properties, physical and chemical properties. And again, physical, really those kind of big things: color, shape, odor, luster, size, melting point, and density. And then obviously what we start with, what we end with is the same. Chemical indicates the ability of a substance to either go through a reaction or resist a chemical reaction. Examples of chemical change: rust, silver tarnishing, and a bunch of other sort of examples. So we want to classify each of these as either a physical or a chemical property. So take a second here and see what you come up with. Okay, so let's take a look here. So we got a few different ones. Let's talk it through here. So ice melting in the sun. So clearly the ice is picking up heat from the sun. Endothermic type process, it starts to melt, becomes liquid water. Again, the ice and the liquid water are still H2O. So that is a physical change. Copper is shiny. That is a physical property. Paper can burn. That is the ability of it to go through a chemical change. Silver knife can tarnish. That definitely is chemical. And a magnet removes iron particles from a mixture. That is physical. So earlier we were talking about sort of a heterogeneous mixture where we had sand and metal pieces in the sand. Clearly, one way you can remove that is simply take a magnet and you can pull out all of the metal pieces. You now would have your metal pieces and your sand in their original forms. Again, nothing has really changed. And again, because it's a heterogeneous mixture, that is a physical type of property. Physical and chemical changes here. We're going to be burning some candles, melting some ice, toasting some marshmallows, cutting a pizza, and we're going to rust out an old car, sadly. So take a second here and see what you come up with, chemical or physical changes in each of these. Okay, so let's take a look. Burning a candle, ice melting. So we should have a chemical change on the candle. Again, the candle starts to melt. Obviously, it forms probably some scents coming off and stuff like that. As it continues to melt and melt and melt, basically as it's basically chemical reacting. At the end, you basically are kind of left with a small puddle of liquid, and everything else is basically burnt off as a chemical change. Ice melting, as we talked about a couple different ways here, physical. Toasting a marshmallow is chemical. Again, you know, if you toast a marshmallow, kind of cooking it, you see maybe some burning on it and some type of substance that is formed. That is a chemical change. Cutting a pizza is physical, and obviously rust, as we talked about, is a chemical change. The next thing we're going to talk about is temperature. And there really is several different temperature scales that we use in chemistry, or that we do see. One is degrees Fahrenheit, one is degrees Celsius, and one is the Kelvin temperature scale. The major difference between these three is degrees for Fahrenheit, degrees for Celsius, no degrees. Therefore, Kelvin, it's just Kelvin. So you say like 373 Kelvin. Out of these three, this is the one in chemistry that pretty much if you have some type of formula that involves temperature, it should probably be in Kelvin. Not too much we come across here in Fahrenheit, but we do see a lot of things in Celsius, and a lot of the conversions we have to do is to take Celsius into Kelvin by doing that conversion. And here's the difference in the three temperature scales. And, we'll see these formulas here in just a second, but really, if you want the temperature in Fahrenheit, you would take 1.8 times the temperature in Celsius plus a 32. If you want the temperature in Celsius, it would be the temperature in Fahrenheit minus 32 divided by 1.8. And the one that we use the most, which would be the temperature in Kelvin, is temperature in Celsius plus 273. This is typically the number everybody uses. The true number is really 273.15. Most people take off the 0.15. If you want to leave it on, you can, but most people just do the 273. And I kind of made a mess there, but it is plus 273. We also sometimes will take the temperature in Celsius by taking Kelvin minus 273, but definitely this one here, temperature in Kelvin, is the temperature in Celsius plus 273, is definitely one in chemistry that we use a lot and a lot. So the differences, between sort of how we convert between these temperature scales does involve where water freezes and water boils on each of these scales. It's 100 degrees on the Celsius and Fahrenheit scale. I'm sorry, Celsius and Kelvin scale, and 180 degrees on the Fahrenheit scale. And that's where kind of the 1.8 comes from. 1.8 is also 9/5 or 9/5 that maybe you learned when you're younger as a fraction to do some of these conversions. When we do problems, typically speaking, and you're just doing a temperature conversion, we do a little bit different in terms of our normal significant figure rules. We actually do the answer slightly different. And it really only applies to sort of when you're doing a temperature to temperature conversion. And that rule is whatever the original value for temperature looked like is how you want to kind of give your converted value. And what I mean by that is, for example, if we had 125 degrees Celsius and we wanted to go into Kelvin. So to do that, the temperature in Kelvin would be 125 plus 273. And if we do that, grab a calculator around here somewhere. There's one. All right. So we got 125 plus 273, and that's going to give us 398. And the units here would be Kelvin. And our original number here was a whole number, which means when we convert it, we do want to make sure that we keep it as a whole number. If I had 12.5 degrees Celsius and I wanted to convert it to Kelvin, I would take the temperature in Celsius is 12.5 plus 273. Now in this case, 12.5 plus 273, I end up with 285.5 Kelvin. In terms of sig fig's original number went to 1 decimal place, we would want to take our converted value to 1 decimal place as well. So specifically just for temperature conversions, whatever the original number looked like when you're doing just a temperature conversion, you want to make the converted number look the same. So if it was a whole number, take it to a whole number. The original number went to 1 decimal place, take it to 1. The original number went to like 3 decimal places, take it to 3 decimal places. So here's sort of what I just wrote there, but basically, how we get to our conversion is the difference between sort of the boiling and freezing points. And that's really where that 1.8 number comes from. What is the temperature at which water freezes? Water freezes at 0 degrees Celsius. And where does water boil? Water boils at 100 degrees Celsius. 100 degrees Celsius, water boils. and 0 degrees Celsius, it freezes. So 0 degrees Celsius where it freezes. We do not see 100 degrees Celsius here as any of our sort of choices. So maybe we need to do a conversion from Celsius to Fahrenheit and Kelvin and see if any of them match. So if we want to convert it to Kelvin, it would be 100 plus 273. That looks like a 373 Kelvin. So that looks potentially good. How do we know it's not one of the Fahrenheit numbers? Well, temperature in Fahrenheit is 1.8 to temperature in Celsius plus a 32 gives us 1.8 times 100 in this case, plus a 32, which means that we would take 1.8 times 100 and add it to 32. And that gives us water boiling on the Fahrenheit scale of 212 degrees Fahrenheit, which obviously is not one of the answers. So that's how we know that it is 373, because that is equivalent to 100 degrees Celsius. How many Celsius units are there between boiling and freezing? 100 is the answer there. So going between Fahrenheit and Celsius, again, is our conversions there that we talked about and I wrote on the previous page. You do need to know how to do the temperature conversions. They will not be provided for you. So just to clarify, you do need to know that temperature in Fahrenheit is 1.8, temperature in Celsius plus 32. So again, that will not be provided for you, nor will the temperature in Celsius be temperature in Fahrenheit minus 32 divided by 1.8. Again, will not be provided to you. Temperature in Kelvin is temperature in Celsius plus 273. And again, if you wanted sort of the reverse of that, temperature in Celsius is temperature in Kelvin minus 273. So these you do need to know, will not be provided for you, in terms of exams or quizzes. So here, if we look at 21 degrees Celsius and we want Fahrenheit, let's take a look at how we would do that. So obviously we want the temperature in Fahrenheit, which is a 1.8 temperature in Celsius plus a 32. That means if we put it in there, 1.821 plus a 32, and where did I throw my calculator? There it is. 1.8 times 21 plus a 32. That is, I think, 69.8 degrees Fahrenheit in this case. Now, this is what we're talking about in terms of significant figures. This guy here is a whole number, which means typically speaking, we would report this to a whole number, and we would probably report 70 degrees Fahrenheit. Again, not to the first decimal place, but because our original number was a whole number, that's where we would take our converted value to. And hopefully they agree, and they do. So 70. The Kelvin scale, as we talked about, is basically 273. The Kelvin temperature scale used to be referred to as the absolute temperature scale. And the absolute zero is 0 Kelvin, and absolute zero, which is 0 Kelvin. And if we do that conversion to Celsius, is Kelvin minus 273, which means 0 minus 273, which means really absolute zero is minus 273 degrees Celsius. It's actually an important number. We'll actually see it in the gas law chapter as well, but that's what's referred to as absolute zero, later renamed after obviously Kelvin because of that. So let's take a second here and give it a try. What is the normal body temperature in Kelvin? So take a second and see what you come up with. Okay, so see here, we have Celsius and we want to go to Kelvin. So again, Kelvin going to be Celsius plus a 273. That would be a 37 plus a 273. And in this case, we would end up with 37, not minus, 37 plus 273. gets you 310. Again, just Kelvin, no degrees Kelvin. So it looks like it should be B. We're okay in terms of sig figs because this is a whole number. We took our answer to a whole number. So everything is good in terms of that. And hopefully they agree with us. So that's good. Let's try another one here. On a cold day, we got minus 15 degrees Fahrenheit. What is that in Celsius? So take a second here and see what you come up with. Okay, so temperature in Celsius is Fahrenheit minus a 32 divided by 1.8. So we're going to go minus 15. It is important the negative here. We want to keep it minus a 32 divided by 1.8. And here, when we take a minus number, which is 15, minus another number, we're basically adding those two negative numbers together because it's like a minus 47 divided by 1.8. Looks like on our calculator, minus 26.1111, a whole bunch of ones, degrees Celsius. What should we report the answer to? Well, if we look at our original number, that is a whole number, which means we would want to take it here. That is a 1, which means we just drop it, which means minus 26 degrees Celsius. Looks like D would be a winner on that particular one. And it looks like they do agree, so that's always good. Here's a comparison of some temperatures on a different scale. And I would say probably outside of this chapter, probably not going to see very much Fahrenheit. It is very common in chemistry to have temperatures given to you in Celsius, but even more common and more needed to convert things into Kelvin. And like I said before, pretty much every single formula that I could think of, there's a few that aren't, but almost every single chemistry sort of formula that has a temperature in it, usually the requirement is that the temperature needs to be in Kelvin. Body temperature, obviously, above 41 degrees Celsius is hyperthermia, hyper meaning more than, right? Which obviously can cause a lot of problems. And heat stroke occurs above 41.1 and try to cool down everybody, put them into ice. Hypothermia is sort of the opposite when we drop below 28.5 degrees Celsius. Again, not a good situation as well. So a person has hypothermia, body temperature 34.8 degrees Celsius. What is their degrees in Fahrenheit? So take a second here and see what you come up with. Okay, so let's take a look here. So we want to go really to Fahrenheit. And that's going to be a 1.8, our temperature in Celsius plus 32. That means 1.8, 34.8 plus a 32. And plus a 32. And again, on our calculator here, 94.64 degrees Fahrenheit. When we look at our number here, we see it actually goes to the first decimal place, which means we probably want to report that to the first decimal place, 94.6 degrees Fahrenheit. A little below there, 96.8, right? So that would be the correct way to report that. And again, they do agree, so always good. All right. So again, on the temperature scales, you do need to know the different temperature scales. You do need to know, obviously, those formulas and how to use it properly. And again, outside of this chapter, probably that conversion between Celsius and converting that to Kelvin is the one you'll probably do 99% of the time. So we're going to talk about changes of state, which we sort of touched upon earlier as well. But let's just go into it just to make sure. As we sort of transition from one state to the next, as was referred to as changing the states, again, as we go from something from, say, solid to liquid to gas, or backwards, obviously, those are all changes of state. Now, melting and freezing, a substance will basically change from solid to liquid at its melting point, and it will change from liquid to solid as freezing point. Water, for example, has a melting point and freezing point of 0 degrees Celsius. So as we were talking about earlier, it actually occurs at the same temperature. So let's just say, for example, here, this is 0 degrees Celsius, and we're talking specifically about water. Right at 0 degrees Celsius, this is like ice. This would be like liquid water. But right dead on 0 degrees Celsius, basically, we'll highlight it. We basically have both phases occurring at the same time. So here we have a little bit like ice crystals in this region. Got a little bit of solid ice, got a little bit of liquid water happening at 0 degrees. And it's not really to get right above 0 degrees or a little above 0 degrees that you transition into really liquid water. It's not until you get a little bit below 0 degrees that you transition into ice. But dead on at 0 degrees, you basically have both things happening at the same time, which is what's referred to as being in equilibrium with each other. And that's why we say that melting and freezing occur at the same temperature, because if you're right here at 0 degrees Celsius, it really does depend on what you're going to do in terms of energy. If you continue to heat it, you will go in this direction and form liquid water. If you continue to cool it at 0 degrees Celsius, you will then go back into ice or release that energy. Now, is there a certain amount of energy to do that transition? And there is. So specifically for water here, when we're talking at that, I'll draw it again here. Liquid, ice, and again, and this is sort of temperature here, 0 degrees Celsius. Dead on 0 degrees Celsius, there's a certain amount of energy that's required to do nothing more than that transition. And that is what is known as the heat of fusion. So the heat of fusion, which is sometimes abbreviated like this, delta H of fusion. Delta H is what is known as the enthalpy. It's a fancy word for heat, basically. But there's a certain amount of energy to do nothing more than to take that substance from the solid phase at 0 degrees to the liquid phase. So we would need to put in 334 joules per gram of water to do that transition. And if we did that, we would be at 0 degrees Celsius, and we would go from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. Not changing the temperature, not increasing or decreasing temperature, but to simply take, for example, water here and change it from solid to liquid would require that much energy. And that's what's known as the heat of fusion. That number works both ways. It would actually be positive, which means it's endothermic, absorbing energy, to go from ice to liquid. If I want to do the other thing at 0 degrees Celsius, go from liquid water to ice at 0 degrees Celsius. Oops, let's write that right. Let's try again. 0 degrees Celsius. It would take the exact same amount of energy, 334 joules per gram. The difference is it would be negative or exothermic. Remember that as we go from liquid back to ice or solid, we have to release the energy as exothermic, giving it off. So the amount of energy required to do that is exactly the same. It just depends the sign, which way you're going, as to whether you're putting the energy in or taking the energy out. The 334 number is specific for water, and also 0 degrees Celsius in terms of melting and freezing point is specific for water. If we were talking about a different substance, then it would be a different number in terms of the melting and freezing point and a different value for the heat of fusion. We also sometimes look at it in terms of calories, or 80 calories. It's the same as a 334 joules. Calorie is a unit of energy. And the relationship between that and a joule is there's 4.184 joules, which is also a unit of energy, joules, calories. And that is the relationship between those. So 80 calories is the same heat of fusion as 334 joules per gram. All right. So for example, if we wanted to know how many kilojoules of energy is needed to melt 32 grams of ice at 0 degrees Celsius, that would be our heat of fusion. And we could very simply use our 32 grams of ice. And we know the heat of fusion is 334 joules per gram. If we do that, the grams will cancel and we will end up with 32 times 334 yields us 10688 joules, but it does want kilojoules, which is a common unit. And there are 1,000 joules in a kilojoule. That's the kilo conversion. We divide that by 1,000. We end up with 10.688 kilojoules of energy needed to melt that amount of ice. Let's talk sig figs. This is really the number we're looking at, which has 3 significant figures. It means we really should go to here. That's an 8, which probably means 10.7 kilojoules would be the correct significant figures way of doing that. And let's see if they agree, hopefully. Yep, 10.7 says good. Now, sublimation and deposition is those processes where we go from solid to gas, or gas back to solid. Here we skip the liquids phase. And a very common thing that does that is dry ice. As you may know or may not know, dry ice is actually carbon dioxide. It's actually not water. It's very, very cold. And the same thing happens, is we go from solid directly to gas. That's endothermic. You need to put energy in to do that. As we go this way. Exothermic, as we go the opposite way, you've got to remove energy or release energy as we go this way. Sublimation, again, is what happens when we have dry ice. Again, it goes from solid to gas, no liquid cleanup. Deposition, for example, if you remember CDs, DVDs are really shiny. They use a process of deposition to deposit metals on top of it to make them shiny in those processes. Talk a little bit about evaporation, boiling, and condensation. Evaporation occurs when really molecules gain enough energy to escape the liquid phase. So, when we do that, it usually occurs at the boiling point. And basically what it means when we start to boil something is, you start to see those bubbles, right? And that kind of works their way up, right? And eventually we get the steam and all that. What's happening is we're heating this up or creating a gas in here. And this gas, in terms of its pressure, at some point needs to be equal to or greater than the atmospheric pressure is pushing down on it, and it's able to sort of escape. But by the process of heating it, we're also providing a lot of energy to these water molecules, allowing them enough energy to escape each other and really go into the gas phase and start to boil and create, obviously, steam. And obviously this occurs at the boiling point, and that's where you see those really big bubbles. You might see, or when you boil water to make pasta or something like that, and you put the water in there and you first hit it with the heat and you see a bunch of like little dots that look like, oh, it's boiling really quick, but it's really not boiling. At that point, what's happening is the CO2 that's probably dissolved in the water becomes less soluble, and that's what you see, those little kind of first dots. It's really not until you get those really good bubbles, that are working their way up, that you really start to get the thing to start to boil. And evaporation and condensation happen again at the same temperature, and that's usually the normal boiling point where this happens. And same idea, as we go from liquid to gas, that is the process of evaporation or vaporization, and that is also endothermic. We need to put heat and energy in. Going from gas back to liquid, which is condensation, that is again exothermic. We need to release heat and energy. And again, happening at the exact same temperature. For example, for water, that's 100 degrees Celsius where this process occurs. Same idea as what I drew earlier. We had earlier this sort of deal at like 0 degrees Celsius. That's where we had our ice, and then we had our liquid water. Same thing happens. We get another transition. And that's really badly drawn, so I'm trying to straighten it out a little bit there. All right, take two. Here we go. Up, then over, and then up. And if this is a straightish line, plateau line, if you will, at 100 degrees Celsius, that's where we go from liquid water basically to steam, which is gas. And exactly at 100 degrees Celsius, just like we talked about at exactly 0 degrees Celsius, exactly 100 degrees Celsius, we have again both of these phases occurring at the same time. So exactly 100 degrees Celsius, we have a little bit of steam, a little bit of liquid water, not to get a little bit above 100 degrees Celsius that you got steam, not to get below 100 degrees Celsius that you have liquid water. And just like we saw with the heat of fusion, there's a certain amount of energy required to do just that transition. So again, that transition where we're going from, gas, steam, basically, to from liquid water. And again, at 100 degrees Celsius, at that transition, that is what is known as the heat of vaporization is required to do that transition. And much like the heat of fusion, we are simply taking something from at 100 degrees Celsius liquid water to steam at 100 degrees Celsius, not changing the temperature or anything like that. That requires about 2,260 joules per gram for water to do that. So if we were going at 100 degrees Celsius liquid water to 100 degrees Celsius steam, it would be positive 2,260 joules per gram to do that. And by the way, this is also sometimes referred to as a delta H of vaporization, or the heat of vaporization. And if we were doing the opposite at 100 degrees Celsius, going from steam back to 100 degrees Celsius liquid water, that's going to be minus 2,260 joules per gram. And that's because that is exothermic. Numbers the same. Sign of negative implies exothermic. Sign of positive implies endothermic. So positive energy value means that the process is endothermic. Heat and energy is absorbed. Negative value for energy means that we have a exothermic process. Heat and energy is released. We also see that it takes a lot more energy. So if you remember this guy, and I'll add this guy in at 0 degrees Celsius. This is our heat of fusion, was 334 joules per gram versus 2,260. Takes a lot more energy to do the transition going from liquid to gas than it does to go from solid to liquid. And that is because when we go from liquid to gas, everybody's 100% breaking apart from each other. It takes a lot more energy to get everybody away from each other. As we go from solid to liquid, which is the heat of fusion, they are away from each other, but they're still relatively close to one another. So a lot less energy is needed to do the transition between solid to liquid than the amount of energy needed to do the transition between liquid to gas. Heat of condensation, same idea, it's just a negative. And so, for example, if we want to know how much energy is released from steam at 50 grams, volcano condenses at 100 degrees Celsius. So this is going through condensation, which basically means we're going from gas to liquid. Technically speaking, that would be negative 2260 joules per gram, because this is an exothermic process. We would take 50.0 grams. We would times it by technically 2260 in the negative version. Grams would cancel. That is our heat of vaporization for water. Again, specific for water would be a different value if we weren't talking about water. Ends up with negative 113,000 joules. We take that and divide it by 1,000 to convert it into kilojoules. And we end up with minus 113 kilojoules. Again, here I put the minus in, probably a good idea, because again, it does indicate that this is a exothermic process. Heat and energy is released as a result of this process. We'll see what they come up with. They didn't actually put the negative here because they in the problem asked about released, which implies exothermic, and that implies a negative value. So let's talk a little about the heating and cooling curve, which is kind of what I've been drawing. A heating and cooling curve basically shows us the changes that occur as we transition from one phase to the next. This is a heating curve. This is solid, that's liquid, and that's gas. Here we see our plateaus, and that's really where we have our changes of state. So this is, for example, is our heat of vaporization. Down there is our heat of fusion. And again, that's really where we have our transitions occurring. So that's our delta H of vaporization. And this little guy over here is our delta H of fusion. Again, that's the energy, as we just talked about, required to do that transition, not really change the temperature. Now, when you look at a heating and cooling curve, those are referred to as plateaus. They're flatlined. And that basically means that when we're at those points, we're at a point where we are not changing the temperature, but we're changing the phase. So we're changing the phase, but not changing the temperature. And when we kind of go the other ways where it's increasing, kind of this way, and down in here, at those points when we're kind of not in a plateau way, we are actually in the same phase, but changing the temperature. So for example, right here in the green where I highlighted, that is 100% liquid all the way through from 0 to 100 degrees, all the same phase, all liquid, but we are changing the temperature. Same thing here from above 100 and so forth above, that is all gas, but changing the temperature. And below here, 0, that is all solid, but just changing temperature. And that's different than in our yellow spots where they plateau. In those plateau regions, they are keeping the same phase. So they stay, for example, they keep the same temperature, but they change the phases. So it goes from, say, liquid to gas, but stays at 100 degrees Celsius. And that's what we see here. This is a kind of a cooling curve going the other way, removing energy. And that's sort of exothermic process. Same idea. We have our places where we are same phase, but changing temperature, which are this part of it. And then we obviously have our changes of phase when we go from in this case, gas back to liquid, but at the same temperature, and liquid back to solid at the same temperature. Heat of fusion, heat of vaporization there needed. So a plateau on a heating curve represents, again, a plateau is our just straight line, not changing the temperature, but changing the phase. So it would be constant temperature and also probably a change in phase, and a slope line, which is the lines that go that way, as we talked about. That's the same phase all the way through, but we are changing the temperature. Use the cooling curve to answer the following. Water condenses at condensation occurs at 100 degrees Celsius. Our temperature at 0 degrees Celsius, liquid water will start to melt or freeze depending on which way you go. At 40 degrees Celsius, that's above 0, but below 100 degrees, that would put you at the slope. Like here's 0 degrees and here's 100 degrees. You'd be in here, and that is our liquid water area. And water will freeze. Water freezes, heat is removed as exothermic. We need to do that as well. So at 0 degrees, at temperature 0 degrees, liquid water will start to freeze. Again, going from that way, I guess is the question, liquid to solid in that process there. Okay, I think we're not going to worry about the rest of these here. Yep. And I think that should be it. I think, yep. All right, so we're not going to worry about this example here. We're not going to do this type of calculation because we're really going to talk about specific heat. So I think you're good on that there. So that should wrap up. This chapter. Again, we're not going to worry about this type of calculation here. So don't worry about it. And that should also wrap up chapter 3. And again, this is a pre-recorded one because we had a holiday and obviously started in the semester. So this will hopefully get us back on track. Obviously, if you have any questions, you can always ask during discussion or whenever we have some time to talk about it. Thank you very much for listening, and I will see you on the next time we are together.